Good morning to everybody. It's a real pleasure to be here. I would like to thank the organizers, especially to Jefferson, my friend from the south of Brazil, a dear friend. So first of all, I have a disclaimer. Although I'm a man talking, and there are extremely clever ladies in the audience, this is not a man explaining talk, okay? And so I'd like to talk about singular diffusion. I come from Fortaleza, Universidade Federal do Ceará, the physics department there. So I have to tell you very good news. Since you stayed here for the last day, up to the end, you have a bonus. My talk will have 2 different subjects. I'll try to do that in 30 minutes if it's possible. So we will also talk about itinerant conductance in fuse-antifuse network. I'll try to make it as quick and easy as possible. So I first have to thank the collaborators that I have there in Fortaleza, starting from André Moreira, Humberto Carmona, they are all professors in our department. Rilder is a PhD student. César Sampaio is a postdoc. And Nuno Araújo is a professor in Lisbon. And Professor Hans Hermann has been a visiting professor there in Fortaleza for many, many years already. So he's from ETH in Zurich. So I start with the BTW model. Most of you know that very well. So this is the beginning of the self-organized criticality subject. And this is the most celebrated paradigm of self-organized criticality published in 1987. It's a very simple model which generated a lot of repercussion in the physics, statistical physics community. So you start in, it's a cellular automaton model describing the interactions of an integer value. So what do you do in 2 dimensions? You have a measurement Z, and you update that in a synchronous way by simply saying, okay, Z, you reduce Z to 4 digits, and you add the nearest neighbors of this position to 1 digit. If Z exceeds some critical value, the real value for K doesn't matter so much, so because it simply represents a shift in the local variable Z. So what he found, Pierre Bach and company, they found that this type of cellular automata is very out of equilibrium system, if I can say like that. So it exhibits avalanches, not only in size, as well as in time durations. So this was a very interesting paper published in 1987, as I said. And the last time I made some investigation, it had more than 4,000 citations. I think it's more than 6,000 now. I'm not sure. Anyway, so this BTW model, it's interesting because in the sense of standard diffusion, this BTW model has a very different meaning, I would say. So what do you do, for instance, in this particular configuration here? So if you are in this stage and you add a single element to the position Z at the stage A, so what happens? So if the threshold is equal to 4 in this particular case, what do? You redistribute all the 4 elements in that position to the nearest neighbors, and what do? You generate a hole in this special point. So when you do that, of course, this does not correspond to standard diffusion. Why not? Because in this particular case, what you have is that you are not trying to attenuate the gradients around that particular point. Okay, so you're not doing that. What is the usual mechanism would do? So usual diffusion, what do? You attenuate the gradients or the chemical potentials, if you wish. So this is not a standard diffusion mechanism. So people realized that much before us. So there's this very nice physical review letters published in 1990 by some theoretical and statistical physicists. So what they did, they found out that it's possible to map this cellular automaton in a nonlinear diffusion equation. So they had a theorem which is not so easy to understand, but not so many pages. It's a very, very small one. So they could derive this rigorous result, and they could find that, okay, you have a nonlinear diffusion equation in which the diffusion coefficient depends on the local density, but more than that, it depends in a singular way. So, so there is a critical point for which this diffusion coefficient would diverge. So I always thought this paper very nice, especially for applications in the sense that these can be very well related with absorption and catalysis in chemical engineering and chemical fields. So there are, for instance, zeolites work like that. They have special diffusion coefficients which depend on the local density in the system, and they enhance the diffusion coefficient. So it's an anomalous type of diffusion, but more than that, singular. So what we did was, okay, in that paper, they didn't manage to find scaling laws for the avalanches. So we thought perhaps we could confine the cellular automaton way with some sort of potential and find out if it's possible to, in an equilibrium state, some sort of equilibrium state, determine whether or not power laws for avalanches can appear or not. So as in that model, so we repeated everything apart from the confined potentials, we have a two-state model. So in practical terms, this is one-dimensional lattice on which you add n particles are placed in such a way that the height of each site is either 1 or 0. So our threshold is equal to 1. So whenever the site is filled, it has to jump somewhere else. At each step, one grain is chosen randomly to move to the left or to the right with the same probability. So we don't argue with that. It's simply arbitrarily taken, so we don't want anisotropy in this process. So if the nearest neighbor is chosen in the chosen direction is occupied, so the grain has to jump to the next one. Okay? So instantly, to the nearest neighbors in the same direction. If it's also occupied, it keeps jumping till the point in which it finds a vacant site. So then you have to apply some sort of metropolis algorithm to find out whether that particle will remain in that vacant site or not. So it will depend on the local difference of potential between the original and the target site that you have. So what do? The external confining potential is applied to the system. This is the beginning of our problem now. So now we introduce a non-uniform transition from site I to J. And for a given transition, what do? We compute the difference in potential energy and use a metropolis, a very simple metropolis rule. So if the difference of potential is negative, you locate the site in the target. Or if this value W here, which is the metropolis factor, if you generate a number between 0 and this number is more than W, where beta is the temperature, it relates with the temperature of the system, so you also allocate. Otherwise, if none of these two conditions apply, so you simply allow the particle to remain where it was. Okay? So it's a very simple algorithm. So you can write a master equation for that in a very simple way. So now instead of using Z, we go for some sort of continuous measurement of the system. So rho of I means rho of x, y, t. So this is a probability that site I is located at a position x, y at a given time t. So you can define a rate of density increase or decrease in that system. So you have two different terms here. The first one is the term which you will have a vacant site at the point E, and you want to bring a particle from right or from left. So we have two different probabilities associated with that. So the first thing is that site has to be vacant. So you multiply that by the 1 minus the density at that site. Of course, all the sites have to be occupied so that you reach the site J. So for you to reach the site J, all the sites have to be occupied, including the site J, so that you have a particle there. Okay, so this is the first term, when you go from right. So when you go from left, it's exactly the same thing. All the sites have to be occupied, but now, instead of using rho of I plus k, you use rho I minus k. I forgot to say that the center of the system is equal to I equal to 0. Okay, yes, sir. No correlation whatsoever. Thank you. Yes. So now you want a particle to go from site A to site J, wherever you want in the system. So this is a different term. So if you go to right, so we have the same thing. Now instead of using the probability of the site J to be occupied, it has to be unoccupied. So that's why you multiply this to the probability of the site rho of I being occupied as well. So it has to be unoccupied, and all the sites in between have to be occupied, so that it will jump till that particular point. Yes. Sorry? It will not. It will not. It's a chemical potential, so you put it in a confined way. Yes. So It's synchronous. It's asynchronous. You do it one by one. Yes, yes, thank you. Okay, so you have, of course, you have some average transition time here to deal with. So this will give us some diffusion coefficient at the end, as we will see. So you can you can start developing it. So you have to calculate every expansion for this minimum of 1 and the exponential of minus beta and the difference of potential between the two sides. So you have these 3 different conditions here depending on the difference of potential between the 2 points. So I will not go into the details of that. So what do? You expand those productory that are on the left of the system to the second order of the distance of the lattice site. So you go for expansion to the second order. So you also expand the exponentials in this way in terms of the potential difference in space. Now this is derivative in space of the potential, okay? So you also expand that to the second order of the lattice distance, lattice space if you want. And then you end up, after some calculations, with 3 not yet differential equations, but for different gradients of potential in the system. So it's funny that they have exactly the same terms, whether or not the signal of the gradient, the local gradient, is different. So when you do that and you group everything, you see that these are redundant and the same. Of course, you have to believe me. And now if you assume that the transitions are continuous in time as well, so you can, and if the square to the lattice space divided by 2 times tau, in the limit where tau goes to 0, goes to a constant, to a finite value, it's not equal to 0. So then you can define something which is not the diffusion coefficient, is a prefactor of the diffusion coefficient itself, because the diffusion coefficient, as we will see, will depend on the local concentration. So you end up with this nice partial differential equation here, which is very similar to what Carlson obtained before in their physical review letters. But now we have a potential term here, which is also presenting some singularity. Of course, this is a weak singularity compared to this one, but it's also singular. Okay, so now it's possible to solve this equation at least to the steady state analytically. That's what we do. So we solve it at the steady state. So what? You can represent that in terms of second law of Fick. So it's simply which is simply a continuity equation. And now the flux is defined in that way from the previous equations that I showed you. So if you define that, and you define a steady state by the partial derivative of the local density equal to 0 with time. And also, you assume that the system is confined so that you have to conserve particles all over the system. So the entire flux, the particles will not escape from the system never, whenever you have a strong or a weak potential applied to this. So you end up with this ordinary differential equation in ρ and the potential that you have to define previously. So, and the final solution for that is very simple, it's represented in terms of that. You have a constant here, which is an integration constant simply obtained by applying that the number of particles is conserved in the entire system, okay? So you have to do that whenever you want to calculate the local density for it. So, of course, this comes from, this is a Fermi type of distribution due to the exclusion process that you have there, the jumps. And what we did for different potentials, we did analytical as well as numerical calculations, as you can see here, for the steady state. And you have different types of potential applied, of confinement potentials applied to the system. And of course, for our happiness, the numerical results agree very well with the analytical results for the continuous differential equations that we developed. So for all different types of potential. Yes? I don't know. No, I'm not sure if people did that yet. Okay, so so this is what we see here. Of course, whenever the potential is more and more intense, like for instance when you go for a kappa, which is the strength of the potential, to 28, you see that all particles group together in the center of the system. So the system is more and more confined. And that's what you see this step type of profile, okay? So there are no fitting parameters here. Yes, some sort of, yes. Clustering. Yes, clustering, yes, I would say that. So the funny thing is that you can also compute analytically for some types of potential. The avalanches from the system. How do you define an avalanches in two-states model? It's simply a jump from sites I and j define what we call an avalanche by simply calculating the distance between these 2 points. Okay, so you can calculate that. I will not go into the details of this. But here you have, for different strengths of potential, different types of curves. And it's typically an exponential decay when you have this calculated for a very low potential of confinement. This agrees very well with solution for kappa equal to 0, so which is also exponential. As you increase the intensity of the field, you will see that there will be a typical cluster, a typical jump, which grows from the beginning of the cluster, which is centered in the system, to the end. So particles can only jump from 2 different places. Either they are very close to the edge of the centered cluster, or they jump from one point of the edge to the other edge. So that's what you see, this type of jump here, which is of the order of the size of the system. Okay. Okay, so now I go to the second topic. Yes. Yes. So the second talk has some motivation here. So the motivation is particle-laden flow through porous media. So what you do here is simply put particles in a porous media, consolidated one, okay? And you allow, and these particles have mass and volume. So eventually these particles will flow through it in a complex flow like this one. These are not the particles which are moving. The white dots here, the white circles here are the stable and fixed particles in the system which represent some sort of disordered porous media. So this is a typical realization of the Swiss cheese model for a very diluted concentration of solid in the system. So if you calculate, if you solve Navier-Stokes equation in this type of system, this is the sort of velocity scalar field that you have, okay, in a local position of this. So in this, if the particles have no mass, you would generate only from the geometry a networks of very tortuous channels. But if you have preferential channeling, when you apply the pressure drop between the two ends of the system, due to some energy minimization or the flow resistance, you have to reduce the flow resistance. You end up with a steady state flow of a single fluid through a porous media with some preferential channeling. Okay, so the particles will tend to flow through these spots here, which are more close to yellow or red, if you want. So these are particles which travel, most likely. These are known massive particles, non-inertial particles, tracers, traveling through the system if you release them following the streamlines. Okay? So in this particular point, so when the fluid erodes and deposits the material, so this is a different realization of the model. Now the particles have mass. They can be eroded from the porous media, and they can as well clog the porous media. Okay? So you can also, so this condition here is not stable and it's not stationary anymore. So the porous media will evolve in geometry. So we have to go for a different type of model to describe it. Either you go for fluid dynamics, which is very complicated, or you go to some sort of electrical analog. So that's what we did. So also motivated by experiments did in ETH in Zurich, Professor Hermann did with his group there, an experiment there in which you have a porous media here made of glass beads, and you inject a solution of particles which are very small compared to the porous space that you have, to the smaller scale of the pore. You inject them through the porous media, and you see, and you follow the pressure as well as the flow rate inside of the system. So just to show you that the system exists really in Zurich, so this is a photography of that. So what they see when they apply this mixture of particles of quartz and water in the system is bursts in the flux of the system as well as in the pressure drop. So they see bursts. So the concentration the flux will, the macroscopic flux in the system will fluctuate, revealing clogs and reopenings. So the system clog and reopen. The pore is a tube packed with glass beads. Okay, but then you also add very small particles together with water in the system, so that it will plug, and the flow field will rearrange, and it will reopen and it reclog. That's why you see bursts. So this is the analog network electrical analog network model that we have here, published last year. That's our paper. And so what we did here was, for the elementary unit of the network, we have a very non-traditional type of electrical device, which we call here a fuse-antifuse device. So in fact, it's a simple ohm resistor, but it has a gap in which the current goes to 0 whenever you are between two values of the voltage drop. Okay? And what do? You put them together in a network, so you apply a voltage drop between the entrance and the end. And the entire network is also connected to the ground through a very high resistance, just to avoid the possibility that you have isolated elements in the system that will never be accessed anymore. So this is some sort of idealization. And, okay, so the electrical analog, as I said, is a regular network. Each site is connected with its nearest neighbor through a fuse-antifuse element. So, and now we have to discuss a little bit the dynamics, because it's not as simple as the diagram shows here. So you have the antifuse regime. You have the fuse regime here, which works exactly as a fuse, but it's reversible, different from fuse that we see at home. This fuse can go back and be reconnected. And the reconnection appears when you go to the antifuse regime. So it becomes a conductor and also reconnects the fuse elementary part of the system, okay? So the dynamics is like that, just to be very precise. So it's a dynamical system. So if G of t is equal to 1, see, if the local conductance of a given element is equal to 1, and the voltage drop in this element is smaller than Vi, so it's a conductor, or larger than Vc, it is a conductor. It means that in the next step of the flow of the model realization, it will remain as a conductor. So the second one is, okay, if G of t is equal to 1, and you are in the region in which the gap exists, so you clog that pore or that resistor. So it becomes an insulator. So the second part of the dynamics is this one. Okay, if G of t is equal to 0, and you are below Vi or in the gap, in other words, if you are below V of c, it remains an insulator. Okay? And if G of t is equal to 0, and you go up to a voltage drop which is larger than Vc, the second threshold, G of t plus 1 is equal to 1, so you reconnect the elementary unit. Okay, so this is the reconnection phase of the fuse-antifuse device. So we have basically two parameters. V of I is embodied in some quench disorder. And V of C is simply V of I times a given parameter factor that we call S here. So the network model has a simple algorithm too. So what do we do? So initially you apply a voltage drop across, in this particular case, we use a tilted square lattice. Why? To avoid the pathological effects that you have between sites that are in a parallel configuration, for instance, in the square network. At each time, so what do? You solve Kirchhoff's law simultaneously, so that the voltage drops in the entire network is obtained, in the entire size of the network is obtained. So depending on the voltage drop and local thresholds of that local unit, the state of each bond, whether it's a conductor or insulator, is determined according to the fuse-antifuse rule that we defined previously. And in the next time step, the voltage drop at each bond are recalculated. We verify again every unit, every elementary unit of the network, and so on and so forth. So this is how you generate the dynamics. So you see a very rich variety of behavior. But it's nice to measure that in terms of global conductance, some sort of macroscopic conductance of the system. So what do? You simply calculate whenever you are in a line which is parallel to the voltage, which is perpendicular to the voltage drop applied, all the voltage drops times the conductance in every elementary unit that's open and that has current passing through it. It can be also at the entrance or at the exit of the system. So for these two parameters that we have here, this is the type of conductance behavior that we have a long time. So we found some sort of behaviors here that I will try to describe you very quickly. So, for instance, in this particular case here, if V is equal to 26 or 1024, if you're in the two extremes, so all elements of the network remain in the conducting state. So yes, sir, 5 minutes, very good. As you can see here, so all the systems is connected because you are in the limits of very low voltage drop or very high one. So all the elements are conducting. So this is the most interesting one, which is the itinerant phase. So the fuse-antifuse elements in this case dynamically change from insulators to conductors and vice versa. And the conductance fluctuates around mean values. But you have to distinguish between two behaviors here. In this case here, 32 and 64, they fluctuate around a value that is finite. It's not equal to 0. So the system is always open, globally speaking. While in the case of V equal to 512, the system fluctuates around some sort of average value as well, but very close to 0. So the system loses its connection eventually. Okay? And finally, if V is equal to 128, you find some sort of global gap condition in which the system exhibits insulator behavior due to a permanent loss of global connectivity. So we have all these types. And finally, you also have, I forgot to say, the global conductance exhibiting periodic behavior, which is this one, which is a kind of trivial behavior, but if you want, I can explain you later. Okay. So movie time, if I have it. So this is for the case in which the conductance, the system loses connectivity from time to time, and the conductance oscillates around 0 and very large values. So whenever it gains global connectivity, it generates some sort of lightning, which goes from the top to the bottom of the system. So the voltage drop here is applied from bottom to top. Okay. It is, yes. So it has to reach percolation in a way. You're right. Thank you. Okay. So it's always like that. I can go ahead. So this is the phase diagram of our system. So the basic two parameters of this phase diagram is the voltage drop, the global voltage drop applied to the fuse-antifuse network, and the magnitude of the gap between the insulator and the conducting phases. So you can see all different types of behavior here. So the itinerant, what we call itinerant phase here, includes as well as a periodic phase. So you have a non-periodic phase here, and as well as a periodic phase. You have an insulating phase here, and a full metallic phase when the system is always connected in the maximum conductance. So in the non-periodic phase, this is a typical snapshot of the non-periodic phase. The red dots here represent the spanning cluster, the percolating cluster of the system. So the system is always connected, as I said to you, and the global conductance oscillates around a finite value during the steady state evolution. So another type of itinerant and non-periodic is this one, when this exactly the one I showed you before, exactly when the system oscillates around a value of global loss of connectivity. Okay? And finally, the system never reaches global connectivity like this one in the insulating phase. The red, as I said, the red spots here correspond to the infinite cluster, which will never reach the other side of the network. So you always remain with the conductance, global conductance equal to 0. So the outlook, in the case of singular diffusion in confined sand piles, we just managed to extend our system to two-dimensional sand piles. The results are very similar. We could predict that analytically as well. But for special schemes of transport, around the sun pile. For the itinerant conductance in fuse-antifuse networks, what I would like to say is that, of course, it's not only a paradigm for the clogging and reopening in flow-through porous media with particle-laden flow, but also it can be used as a versatile electronic state. So you can devise, really, a fuse-antifuse element like that using electronical apparatus. So it's, of course, a possible description for particle-laden flow through porous media. We're trying to match our results with those that has been produced in ETH. And apparently, there is some similarity with the dynamics of braiding rivers that we would like to analyze. Thank you very much.